In this lesson, we're going to look at an integration technique called integration by substitution. And as we'll see, this technique will greatly expand the types of functions that we can find antiderivatives for. It's a very commonly used and useful integration technique. We'll also see that it is derived from the chain rule. So let's start by assuming that we're given a function, little f of x, and we know that capital F is an antiderivative for little f. And let's also assume that we have another function g of x, which is differentiable. Now recall from the chain rule that the derivative of capital F of g of x, the derivative of this function, is going to be f prime of g of x times g prime of x. Now that's using the chain rule, and going from here to here is basically stating that d dx of f of g of x, just treat the g like the letter u. We often use the letter u in the derivation of the chain rule. This is the same as d dg of capital F of g times dg dx, and you just obtain f prime of g, and g is a function of x, times g prime of x. Okay, so that's how we go from here to here. And now since capital F is an antiderivative for little f, we can replace the capital F prime with little f. So we have that the derivative of capital F of g is equal to little f of g times g prime. So therefore we have this result down here. We then have that the antiderivative for little f of g of x times g prime of x is equal to capital F of g of x, because after all, by this reasoning up here, the derivative of the right-hand side, if we were to differentiate it, we get back the integrand here if we differentiate with respect to x. So let's make this observation now. So if we let u equal g of x, then we have that du will equal g prime of x dx, and that's because if we let u equal g of x, notice that du dx equals g prime, and then just think of multiplying the dx over. So we get du equals g prime of x dx. Then we can write this equation up here as the following. So notice the u is g of x, and du is g prime of x dx. So the du right here is g prime of x dx, and on the right hand side the g is replaced with the letter u. Okay, so what we found here then is that if we are faced with an antiderivative that looks like this, if we make the substitution u equals g of x, then we can turn this into something that looks like this. And if we know capital F is an antiderivative for little f, then we know that capital F of g of x will be an antiderivative for f of g of x times g prime of x. So basically, the moral of the story here is that by doing a substitution, we can turn a rather difficult looking indefinite integral like this into something that is perhaps a little bit easier to integrate, which looks like this down here. Now let's take a look at a few examples and we'll clarify what's going on here. So here we want to evaluate the indefinite integral of x squared times x cubed plus 1 to the 10th power dx. So what we want to do here is somehow relate this to what we just saw. And we want to pick u to be something in here strategically so that we can turn it into something that looks like this. And hopefully, it's not guaranteed all the time, but hopefully this will be easier to evaluate than this. So what we're going to do here is we're going to let u equal x cubed plus 1. Then du will be, notice all we did is differentiate the right-hand side. Now if you look at this up here, the x squared dx, we have an x squared dx right here. If we take the 3 over to the other side, we see that we have du over 3 equals x squared dx. And so we can replace the x squared dx with a 1/3 du. So this integral then will become so you see u to the 10th power came from the fact that x cubed plus 1 is u and x squared dx is du over 3. And now this is equal to and now you see this is our f of u du right here. And this is fairly easy to evaluate. What we get is antiderivative of u to the 10th power is going to be u to the 11th power divided by 11. And then we can just simplify this to, and also we'll substitute what u is. U is x cubed plus 1, so we'll substitute that back in for the u, and we get our answer. And there we have our answer for the indefinite integral of x squared times x cubed plus 1 to the 10th power. Let's just check out if we differentiate this that we get back our integrand up here. So if we differentiate this, notice that we're going to have to use the chain rule, and so that shows you why integration by substitution and the chain rule are really one and the same. So letting u equal x cubed plus 1, you see when we differentiate this with respect to u first, we drop the 11 down, so we're going to get and then we have to multiply it by the derivative of u, which is the derivative of x cubed plus 1, so that's going to be, and simplifying this, we get x squared times x cubed plus 1 to the 10th power, which is what we wanted. And there we go. So see, the moral of the story here is sometimes you can let u be a piece of your function up here in such a manner that du will become the rest of it, and then you'll turn it into something that is hopefully a little easier to integrate. Let's take a look at a few more examples. Now for this problem, we see that we actually have a definite integral to evaluate, and we're going to do this with substitution as well. Now if we look at this, we see that we have an x cubed in the numerator dx, and then in the denominator we have x to the 4th plus 1 squared. Well, notice the derivative of x to the 4th is a multiple of x cubed. So that tells us that we can use a substitution where we let u equal x to the 4th plus 1. So then du And moving the 4 under the du, we can think of this as 1/4 du. And so we see that the x cubed dx actually becomes our du divided by 4. And we see that the x squared, x to the 4th rather, plus 1 is our u, and then that is being squared. So the definite integral using this substitution will then become now we need to change our limits of integration. They're not going to be 0 and 2 anymore. The 0 and 2 were only when we were integrating with respect to x. Now we're going to integrate with respect to u. So notice that if x is equal to 0, u will equal 1. So really we need to put down here in our lower limit, we actually need to put u of 0, which is 1 in this case. And in our upper limit, when x is 2, u is going to be 16, that's 2 to the 4th, plus 1, so that's going to be 17. So in our upper limit, we get u of 2 equals 17. You must remember to change your limits of integration when you do substitution. And this will simplify as, now we're going to move that 1/4 outside, so we're going to write this as 1/4. The definite integral from 1 to 17 of 1 over u squared du. And now remember how we find an antiderivative for 1 over u squared. We think of that as being u to the negative 2, right? So this is, we think of this as being u to the negative 2. And so we're going to get, now the antiderivative of u to the negative 2 is going to be negative u to the negative 1, right? See that we add 1 to this negative 2 right here. We add 1 and we get negative 1. And then we need to divide by 1 over negative 1, or just multiply by negative 1. So this is going to be and then we get 1/4 times negative 1 over 17 minus negative 1 over 1. And that will simplify out to 1/4 times, let's see, this is going to be 1 minus 1 over 17. So it's going to be 17 over 17 minus 1 over 17. That's going to be 16 over 17. And that simplifies to 4 over 17. And so that's our answer. That is the value of the definite integral from 0 to 2 of x cubed divided by x to the 4th plus 1 squared. Now just one note here. Sometimes at this point right here, you may see some people or textbooks put what x is back in place of the u. Now if you do that, then you must go back to the original limits of integration. So if we were to substitute x to the 4th plus 1 back in for u at this point, we would have to write this as so we would have to go back to the original limits of integration. And notice if we do that, we will still get the same result as we do right here. Notice if we substitute 2 in for x and 0 in for x, we're going to get, now if we put 2 here in for x, we're going to get 17. And if we put 0 in for x, we're going to get 1 in the denominator, and we have that negative up there. So, and you see we actually get the same thing as we did over here. So sometimes you'll see textbooks or people go back to the original x values, and if you do that, you need to then use your original limits of integration. And let's just continue with a few more examples. So now here we want to find the indefinite integral of sine of 3x times cosine squared of 3x. Now notice that this is the same as writing Now we need to see if we can find a u so that when we do a substitution, du will become another piece of this integral. Well, we recall that the derivative of cosine is sine, so perhaps we can do this as our substitution. And let's see if that works. So if we let u be cosine 3x, notice that du then becomes Notice we had to do a little application of the chain rule here. We had to differentiate this with respect to the inside 3x term, which is negative sine of 3x, and then we needed to multiply by the derivative of 3x, which is 3. Now we see if we divide the negative 3 under the du, we get And so now we see that we've recovered this piece of the integral, the sine of 3x times dx. So it looks like this substitution will work. So with this substitution, if we let this be our u, so this is going to be u, then du divided by negative 3 will become the sine of 3x dx. This indefinite integral then becomes which we can write as and that is equal to remember the antiderivative of u squared is u cubed over 3. And we can clean this up a little bit and put what u is in terms of x back in place of the u here, and we get and there is the indefinite integral of the sine of 3x times cosine squared 3x. And you can check if you differentiate this, you will get back our integrand up here. Now let's take a look at this one. So here we want to find the indefinite integral of x divided by the square root of 2x plus 1. So now this one isn't quite as obvious what we should let u equal. This one is a little tricky. This one is a slight variation of integration by substitution, so it may not immediately be obvious what we should let u be. Well, in this case, we're going to let u equal 2x plus 1. Now watch what happens. So we get du equals 2 dx. Now we don't have a 2 dx up here. It would be nice if we had a 2 right there, or just a constant would be nice. But we don't have that here. So what we're going to do is we're going to do a little trick. We're going to rewrite the leftover x here in terms of u, and then put that in here for x. So using this equation right here, notice that we can write, if we take the 1 over with the u and then divide by 2, this is what we get for x. Now let's substitute this in terms of the leftover x up here, and what we get is this. So that x in the numerator is going to be the dx from this piece right here. Our dx is du over 2. And then in the denominator we have our square root of u. Now let's clean this up. 1/2 times 1/2 is going to be 1/4. We'll move that outside. Now we're going to use a trick here where we split this fraction apart. So we're going to write it as Now u divided by the square root of u, that's just u to the 1/2, or the square root of u. This is u to the negative 1/2. Now we can integrate each of these using the power rule for integrals. And so this will become, let's see, the first term is going to be u 1/2 plus 1. That's going to be u to the 3/2. And then we need to multiply that by 2/3. That's the same as 1 over 3/2, or if we think of differentiating this, dropping the 3/2 down, the 2/3 will cancel with that 3/2. If we add 1 to the negative 1/2 here, we get u to the positive 1/2, and then we need to multiply that by 2. 1 over 1/2, or think of differentiating u to the 1/2, we would drop the 1/2 down, and we have to counteract it with something, so we would counteract it with a 2, because 2 times 1/2 would give us 1 back. Now we just need to substitute what x is in terms of u back in here, and we'll have our answer. Let's see, u is 2x plus 1, so this is going to be and we can clean that up a little bit if we think of factoring out a 2. In fact, we can also factor out a 2x plus 1 to the 1/2 power. We'll take it one step at a time. So let's write this as Now this is perfectly fine for an answer. However, you might see some textbooks do this. Thinking of the 3/2 here as being 1 plus 1/2. Really what you have here is 2x plus 1 times 2x plus 1 to the 1/2. And then we have another 2x plus 1 to the 1/2 over here. So we could think of writing this as follows. 2 over 4 is 1/2. Now if we factor out a 2x plus 1 to the 1/2 power, what we would have left inside then would be now you see 2x plus 1, the square root of 2x plus 1, times 2x plus 1 gives us 2x plus 1 to the 3/2, and the square root of 2x plus 1 times 1 gives us back the square root of 2x plus 1, and then you can simplify what's in here and write this as. Now let's see, 1/3 times 2x is going to be 2/3 x. 1/3 times 1 is 1/3 minus 1, that's going to be minus 2/3. And then we could even factor out a 2/3 and move it outside and finally write this as. And there we have our final answer. Now we did a lot of simplification here. Usually it's all right to leave your answer in a form, an earlier form like we had up here. But it is good to practice simplification because sometimes you'll look up an answer in the back of the book and you want to check your work, and the author will usually put the answers in a simplified form. So it is good to practice simplifying your answers. And that concludes this lesson on integration by substitution.